Doctor.
Okay, hope you are doing well today. Okay, right. So let us proceed with lecture 5, a continuation from our lecture yesterday on absorption. Okay, in optical fiber. So I just want to recall the things that we have learned yesterday. So we have actually learned about the basic of attenuation. Okay, the formulations of attenuations. And we have also understand about the factors of attenuation. So far, we have learned about the absorption. Okay, we have also learned about the linear scattering. Okay, and I believe that by now you have understand why for mono-optical communication we are working at 1.55 micrometer wavelength. Okay, which is due to the small loss offered by this wavelength, particularly due to low loss of the glass absorption, a low loss due to relay scattering, and also a low loss due to hydroxyl ion absorption. Okay, so these are the things that we have learned yesterday on the attenuation so far. Okay, so for today, we are going to continue on this effect of absorption, factors of absorption, which is the second part of scattering, which is also known as a nonlinear scattering. Okay, yesterday we have learned that there are two types of linear scattering. Okay, two types of linear scattering. And the first one is, I need to admit one of the students that want to join the class. Okay, so we have, sorry for that. Okay, there are two types of linear scattering effect. The first one is Rayleigh scattering, okay, which is particularly due to a small size of impurities or inhomogeneities. And the second type is Mie scattering, which is due to larger size of impurities. Sorry, I need to go back to this Mie. Okay. Okay then, Mie scattering due to a larger size of impurities, right? And we have learned yesterday that, for example, Mie scattering, some sort like a roughness, roughness at the core and cladding interface. Okay, that should be one of the factors that contribute to the Mie scattering. Okay. So for the nonlinear scattering, basically it occurs at high optical power transmission. Okay, normally for high optical power transmission, normally for laser. Yeah, so for laser based application in which we are using laser as a power source or optical source. So the nonlinear scattering will be dominant. Okay. And basically, fundamentally, it is associated with the interaction of light with a vibrational energy of a molecule structure. Okay, so it's more towards the effect of this. When you have a light, it interacts with the molecule lattice of the medium. Okay, so we're going to have a vibration, and this is the effect in which we are going to have a scattering. But remember that in this particular case, the light is scattered at a different frequencies than the incident light. Okay, so that's the difference. So that's what meant by nonlinear scattering, because if you have linear scattering, if you have a wavelength, let's say a wavelength of lambda naught, which is the incident wavelength, so the response, the affected light will also be having same wavelength. But for the case of nonlinear scattering, if we have, let's say, incident power of lambda naught wavelength, so the scattered light will be having different wavelength. Okay, so this is what we call as a nonlinear scattering. Okay, so I put it here that the light due to nonlinear scattering will be scattered at a different frequencies to that of the incident light. Okay, so that should be a difference between linear scattering and nonlinear scattering. So hopefully you understand about the difference between those two. Okay, so there are two types of nonlinear scattering that we that is actually studied in this optical-based communication. The first one is stimulated brilliant scattering, SBS. Okay, and we also have another one which is stimulated Raman scattering, SRS. So basically, brilliant and Raman are the name of the scientists. So these scattering, they are those who invented or not invented, those observe this scattering effect. Yeah. Okay then. Okay. So it can be said that okay, I did mention here that SRS and SBS will observe at high optical power densities. Yeah, and it is actually much affected. Yeah, much affected the transmission that based on single mode fibers. Yeah, single mode fibers. While single mode fibers, I'm going to explain about this later on. Yeah, but for the time being, we agree that this knowledge scattering, the SRS and SBS, it is very much affected a single mode fiber, which is actually used for a long distance transmission. Yeah, because for long distance transmission, normally we are using laser as the optical source. Yeah, okay, not laser, not LED. Yeah, so we have two sources that can be used in optical communication. We have LED and we have laser source. So that should be learned in chapter 4 later on. So for a long distance transmission, the laser will be applied. Okay, and normally for a laser, it will produce a very high optical power. Yeah, and that is why the SRS and the SBS are dominant in the laser transmission, which is particularly used in the single mode fiber. Okay. Okay. So the good thing about SRS and SBS is that they provide or they give optical gain, means they amplify the signal. But the drawback, the drawback of this SRS and the SBS is that the effect will be the shifting in the frequency or the wavelength of operation, which is actually unwanted. Yeah, because we actually in the transmission we want that if we transmit a lambda naught wavelength, so basically at the output we also want the same wavelength. Okay, but these SRS and SBS, although it provides optical gain to the transmission, that amplify the signal, it assists in the signal amplification, but the problem is this shifting of the wavelength. So this is the unwanted things that we don't want in optical communication. Okay, so the effect will be when we have a shifting in wavelength or frequencies, it will definitely contribute to the attenuation for the light transmission at this operating wavelength. Okay, so hopefully you understand the fundamental, the basic understanding about the nonlinear scattering. Yeah. Okay. Okay. So this is the equation that that gives us the threshold power for both SBS and the SRS. Okay. So these equations up here is the threshold power for the SBS scattering. Yeah, SBS, and this is the threshold power for the SRS. Okay, so from this equation, we have a D, yeah, we have D, a lambda, we have alpha, and also V for the threshold power of SBS, whereas for a threshold power of SRS, we have D, lambda, and alpha as the variables, yeah? Okay, so these variables can be stated here that D is the fiber core diameter, okay? Lambda is the operating wavelength. Alpha dB, alpha is the attenuation of the fiber, yeah, which is a standard attenuation of the fiber, which is actually defined or stated by this manufacturer. So when we buy the fiber optics, normally it will be stated in the fiber optics specification what is the attenuation of this fiber. Okay, and the V, which is a light source bandwidth in gigahertz, yeah. Okay, what is a threshold power basically? Okay, threshold power is the value of optical power level that shall be avoided. Yeah, that shall be avoided in the optical power transmission so that we can eliminate the effect of SBS and SRS. In other words, it can be said here that in optical optical communication, this optical signal level, okay, this is the input signal, input signal, or the pump in signal from the laser. The value of this power level must be below this threshold power. Okay, remember? Okay, I repeat again. In communication, in fiber optic communication, the transmitted power, which is produced by the laser source, okay, power level or the signal level must be always below this threshold power, both the PB and PR, so that we can eliminate the effect of these SBS and SRS in the fiber optics communication. Okay. Yeah, so this is the value of PB and PR. Okay, so we just use this equation. So we are not going to define, or we are not going to explore how we get this equation. So we just agree that Mr. Brilwin and Mr. Raman has come up with this equation of threshold power that shall be obeyed. Yeah, that shall be obeyed in order for us to eliminate, yeah, the effect of those SBS and SRS in our fiber optics communication system. Okay, and I did mention here that the SBS and SRS are not actually observed in multi-mode fiber. So we did mention in the previous slide that the effect is severe in single mode fiber. Yeah, so not in multi-mode fiber. Because why? Because due to large core diameters, yeah, the D is the fiber core diameter. So we have learned in chapter 2 that for multi-mode fiber, the core diameters is about 60 something or 80 something micrometer, which is quite big. So for that particular insertion of core diameter in this equation, the value of threshold power, PB and PR, will be extremely high. So basically the pump power level, yeah, the laser power that we pump in the fiber optics structure will not be as high as the threshold power calculated in the multi-mode fiber. Okay, so you got the point there, yeah? Can I repeat again? Yeah, for these SBS and SRS, the nonlinear scattering, the effect is not critical in multi-mode fiber due to the case that these multi-mode fiber is having large core diameters. Yeah, when we compare, when we see these equations here, yeah, note the equation here, we have the D is the diameter. So when we insert the D in these equations here, we can say that the value of PB and PR will be very high. Yeah, will be very high, so that the pump in power laser will not, yeah, definitely will not achieve this threshold power. Yeah, so by that we can say that for multi-mode fiber, this effect of nonlinear scattering is not that critical. So it can be ignored in multi-mode fiber application, but it is critical, it is severe in the case of single mode fiber transmission. Okay then, hopefully you are clear about this statement, yeah? Okay, I have to admit one person need to get in the class. Oh, nobody, yeah. All right, never mind. Okay then. Okay, so I think we have done with the intrinsic factors of attenuation so far. Yeah, intrinsic factors include the absorption. We also have linear scattering and nonlinear scattering. Yeah, so now we are going to learn about the extrinsic factors of attenuation. Okay, so we have learned yesterday that extrinsic factors is about the something that is uncontrollable. Yeah, something is due to the manufacturing effect. Yeah. So these are the examples of few extrinsic factors that can be considered in fiber optics that will lead to attenuation of the fiber. The first one is cable manufacturing stresses. Okay, so basically this is about the imperfections, imperfections in the waveguide structure. Okay, for example, we have a non-uniformity in the size and shape of the core. Yeah, somehow, let's say we have a 6 micrometer core diameter. So we're not going to get very uniform 6 micrometer diameter along the fiber optic structure. Somehow there should be non-uniformity of this core size, of this core size and also shape. of the core. So all of this is the defect in manufacturing, which is uncontrollable. Yeah, we try to make it perfect, but definitely we cannot get it. Yeah, we cannot get it. Okay, and then also due to the perturbations, yeah, perturbations in the core and cladding boundary. Yeah, perturbations, what I mean by perturbations, so I put it here. Okay, this is the diagram which shows the imperfections. Okay, we can call this as perturbations in the core and cladding boundary. Okay, this is also due to this manufacturing defect. Okay, and all of this is produced during this manufacturing process. Yeah. Okay, and also the second one is the environmental effects such as temperature variation, stresses. So all of these will produce attenuation, because as we can define, or as can we see from this diagram here, these particular stress, yeah, due to the external forces on these fiber optics will incur somehow a disturbance on this boundary, and from these imperfections, from this disturbance, we can see that the light which is said to be propagating in the core will be then radiated in the cladding. So radiation of modes in the cladding will incur loss. Yeah? So we have seen this yesterday. Same things happen to these imperfections at the core and cladding boundary. The light will be scattered, yeah, to this cladding, which will further incur loss and attenuation. Okay, so this is a sample, the example of the extrinsic factors of attenuation, which is majorly due to this manufacturing defect. Yeah. Okay, number three, we also can consider the bending. Yeah, maybe during our process of fiber installation might be, yeah, when we start to install the fiber, we lay the fiber in the cable, yeah, in the ground or in the sea, might be that there should be somehow a bending occur, yeah, physical bending occur, yeah, and this bending do incur a loss, yeah, to the light transmission. Okay, and we can define that there are two types of physical bending. We have number one is a microbending, and number two is macrobending. Yeah, micro and macrobending. Okay. All right. So what is microbending basically? So this is the figure that states the macrobending effect. Okay, and basically it results due to macroscopic imperfections in the fiber optics geometry. Okay, so we can see from this diagram here. Yeah, micro. Yeah, the word micro means it's very small. Yeah, very small. So somehow we can define that the microband is somehow look like this. Yeah, look like this, where we have a ripple. Yeah, a ripple on this on the fiber optics structure. Yeah, and the ripple is known as to be a microband. So due to this microband, we can say that the light will not fully propagated in this core structure, but somehow it will be radiated, it will be propagated in the cladding, and it will actually decay, yeah, as a radiated or leaky modes, yeah, in the cladding structure. Okay, so this is the case of this microbending effect, yeah. So this is also the effect of microbending. You can see the bending at the core and cladding interface. So due to this bending, you can see that the light is scattered somehow into the cladding. So the discussion is similar. Yeah, it's similar to the previous one. Sorry. We'll try to get in the class. Okay, never mind. Okay then, let's continue. Okay, discussion is also similar to what we have learned before this, yeah. For example, when we discuss about the mis-scattering, right? The mis-scattering, where we have a roughness at the core and the interface. So somehow the effect is almost similar, yeah. The definition is different, but the methodology, the flow on how the light is scattered is same. Yeah. So when we learn about the misscattering, the effect is due to the surface roughness, the size of the impurities. Yeah. So it will incur, the light will be scattered and it will be radiated into the leaky modes and it will incur loss. And for the macrobending, for examples, we have this structure, which is not uniform. Yeah, the macrobend is not uniform. So due to this bending, the light will not propagate, will not in the modes of total internal reflections. Yeah, so the light incident will be less than critical angle, and as such, the light will be then leak into the cladding. Yeah. So somehow these are the things that incur losses to this fiber optics transmission, yeah, the microbending. Okay, so hopefully if you're being asked to explain about the microbending phenomena, about the scattering phenomena, so hopefully you can do it, yeah? Yeah, you must be able to explain, at least understand this effect that contribute to the attenuation of the fiber optics. Okay, then we have a macro bending. So this is a large scale of bending. Okay, so I put it here, the diagram that shows the effect of macro bend. Okay, when we have a macro bend structure, we can see that the light that is actually in the radiated mode. Yeah, so this is radiation. So this is I can say this is a guiding mode. Yeah, guiding mode somehow guiding mode. So due to this bending, the light will then not obey the total internal reflection, and it will be leaked to this cladding. Yeah, when it leaks to the cladding, so it will then convert it to a leaky mode or radiation mode, and this will incur the loss. Okay, so this is how the macro bending incur losses to the fiber optics. Yeah. Okay. So I put it here that the macrobending is the result of bends or curve in the fiber that give a losses, yeah, radiation losses. Okay, so this is the exact words to be used in which radiation loss just now due to this leak guiding mode, yeah, guiding mode is leaked to the radiation mode, is due to the energy in the evanescent field at the band that exceeds the velocity of light in the cladding. Okay, so this effect, this velocity of light, yeah. So I can say that the best word, the best thing to explain or describe about the macrobending is the existence of this radiation loss due to the conversion of guiding modes to the radiation modes, yeah, as the effect of this bending. Okay, so we can actually see that there should be effect of the critical radius of curvature, yeah, in which for this critical radius of curvature, RC, a large macro bending losses will incur. Okay, so RC is the radius in which by calculating of these terms here, we can calculate what should be the critical radius of curvature that will incur macro bending losses. So as such, we must try not to have a bending up to this radius of curvature. Yeah, so it can be said that this is a threshold value, a conditional value, in which you need to bear in mind, or we need to bear in mind when we design or when we work on the fiber installation. Try not to bend the fiber up to this critical radius of curvature. Okay, and radius of curvature, RC, is given by this equation, 3n1 squared lambda, and 1 is the core index, lambda is the operating wavelength, and n2 is the cladding index. Okay, so basically this is the equation radius of curvature for a multi-mode fiber, yeah, a multi-mode fiber. For single-mode fiber, there's the equation, but I'm not going to cover that in this lecture. Yeah, so what we have here is the equation of critical radius of curvature for a multi-mode fiber. Okay, any question? I think that's done with the attenuation. Okay, so up to now we have learned there are few factors of attenuation: absorption, linear scattering, nonlinear scattering, extrinsic effects, which include the bending, yeah, macrobending and macrobending. Okay, any questions so far on these issues of attenuation? So far,
No.
no. No, yeah? Okay. If there's no questions from the floor, let us proceed with these examples, yeah, which are very much related to the attenuation. So what we have here is very simple example, yeah, very simple example, which is the basic mathematics. Basically, we want to calculate the attenuation, related to the attenuation coefficient, okay? Okay, this slide shows that we have two examples. Yeah, the first one is that we are having input power of 1 milliwatt. The length of the fiber is 1.3 kilometers. Okay, and the attenuation coefficient alpha is 0.6 dB per kilometer. Okay, so we need to find the output power. Okay, the second question is we have input power of 1 milliwatt, length of 2.6 kilometers, attenuation coefficient is 0.6 dB per kilometer, and the output power. So basically the question is almost similar. The difference is the length is different, yeah? Okay, so for this, you need to adopt the equations that we have seen yesterday on the calculation of attenuation coefficient alpha, remember? Yeah, alpha is 10 log of power in over power out divided by the length. Okay, it's a very simple example, but I just want to ensure that you really understand this attenuation coefficient, yeah? Okay, let's have a look at the solution for this example. Okay, hopefully you can see this slide clearly, yeah? This is solution for lecture 5. Okay, so we are given the P in, if you can recall from the example before, the power input is 1 milliwatt, the length is 1.3 kilometers, and the alpha is 0.6 dB per kilometer. So from this is the equation, yeah, that we have seen yesterday, that the alpha, the attenuation coefficient is defined to be 10 of log 1 milliwatt, which is the power in over the power out, and divided by the length, yeah. So by this manipulation of the equation, we can find out that this P out, or the output power, measured after 1.3 kilometer length of the fiber is 0.836 milliwatt. Okay, so this is the output power measured after 1.3 kilometers of the fiber, yeah. Okay, the same thing applied for the second example as before. We have about the same question, but the length is now changed to 2.6 kilometers. So 0.6 dB per kilometer is the coefficient. So 10 log input power 1 milliwatt over the output power divided by 2.6 kilometers. So end up you are going to have the output power is 0.698 milliwatt. Yeah. So as the distance increase, we have shown here as the distance increase, the output power will be reduced significantly. Yeah? So this is something that is known. Yeah, we have learned this basically in this PCOM in third year. So we are repeating the things here. Yeah, but the domain is different. We are dealing with the optical fiber communication system. Yeah. Okay, so let's have a look with the second example here. Okay, so it's about the same questions, but we change the scope a bit. We have the input power of 1 milliwatt, yeah, as shown in this diagram. The input is 1 milliwatt, the output is 250 microwatt, okay, and the length of the fiber is 2 kilometers. Okay, so the question is find the coefficient alpha, okay. So this is straightforward, I believe. The alpha will be equals to 10 log power in over power out, yeah, 1 milliwatt over 250 microwatt, yeah, and the results of that logarithmic value will be divided by 2 kilometers, and that will give us the alpha, yeah. Okay, the solution is there in this slide, PDF slide just now. So I won't show to you, I won't give to you in this presentation, but you can have it, or you can have look at it after the class, yeah, because I'm going to forward the solution after this. Okay, let's proceed with this next example here. Okay, we are having a case whereby there is a optical power launch into 8 kilometer length of the fiber, which is 120 microwatt power, and the mean optical power at the fiber output is 3 microwatt. Okay, got the point here, yeah? So we have a fiber optics communication system which is having 8 kilometer length of fiber optics. The input power is 120 microwatt and the output power is 3 microwatt. The first question is determine the signal attenuation per kilometer for the fiber. So basically this is to find the attenuation coefficient, yeah? Is to find the alpha. Number 2 is to overall signal attenuation or the loss in decibels through the fiber assuming no connectors or splices. Okay, number 1 is to define the alpha. Number 2 is to obtain the total attenuation in 8 kilometer length. Okay, and number 3 is to obtain the attenuation for a 10 kilometers length. Okay, now it's 10 kilometers length. Sorry, yeah, I need to go back to this Google Meet. Student want to add into the class. Sorry, nobody, yeah? Okay, never mind. Okay, we go back to this presentation. So we have a 10 kilometers length now, but the same fiber is applied, but there is a 1 kilometer intervals which is defined by a splices. So what is splices basically? Okay, I'm not going to cover this in our lectures. Splices basically is connectors, yeah? It's a connectors, but it is a permanent connectors, yeah? Splices is a permanent connectors. When you want to connect two fibers, yeah? When you want to connect two fibers, we need to splice the fibers. Yeah, we need to splice the fiber. So the splices basically is a connector which is permanent. Yeah, it's permanent. Right, yeah, okay. Right, so when we have a splices which is when we have a splices which is actually of 1 kilometer length, 1 kilometer intervals, and each of these splice will give attenuation of 1 dB. So we need to obtain what should be the overall attenuation for this 10 kilometer optical link with the splices at every 1 kilometer intervals. Okay, yeah? All right, so hopefully you understand the questions clearly. Right, so let's have a look at the solutions for this example. Okay, the solution from previous question. Okay, this is the one. Okay, we have 8 kilometers fiber optics length. The input power is 120 microwatt and the output power is 3 microwatt. Okay, so for the first case, we are assuming that there are no splices in the structure. So straight away we can calculate that the alpha, the coefficient of attenuation, will be 10 log input power 120 microwatt over the output power 3 microwatt over the length, which is 8 kilometers. So from this calculation, we are getting the alpha as 2 dB per kilometer. Yeah, that is the attenuation coefficient for this fiber. And in terms of total attenuation, total attenuation, we can see that when since we have 8 kilometers length, so total attenuation simply will be 8 kilometers multiplied with the alpha, which will give us 16 dB of attenuation. So for the 8 kilometers length of the fiber, the total attenuation without any splices, the total attenuation value will be 16 dB. That will be total attenuation of the signal transmitted in this fiber optic structure. Okay. So for the third question is that we have a 10-kilometer link, yeah, and for every 1 kilometer interval there is a splice, yeah. So this is a diagram that I sketched to ensure that we can define where is the placement of these splices. Okay, so the TX is transmitter, the laser source or the power source, and RX is the detector where we detect the signal. So there should be 1 kilometer. So 1 kilometer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10-kilometer length, yeah, of the fiber optics structure. And for every 1 kilometer, there should be one splice. So basically for this 10-kilometer length, the number of splices will be 9. Yeah, there should be 9 splices connecting the fibers, yeah. So 1, 2, 3, 4, 5, 6, 7, 8, and 9 splices overall. Okay, so for that, we know that one splice will give us 1 dB loss. Yeah, one splice will give us 1 dB loss. And for the 10-kilometer fiber, the total loss due to the fiber itself, yeah, fiber itself will be the length 10 kilometer multiplied with the coefficient, which is 2 dB per kilometer, which has been calculated in the first part of this question. Yeah, so the length multiplied with the coefficient will give us the total loss due to the fiber, and the total loss, the loss due to the splices will be 9 splices times 1 dB each, and it will give us 9 dB. So the total loss in the fiber will be 29 dB, which is the summation of the fiber loss and the splice loss. Okay, so that should be a total loss in the fiber optic structure. Okay, yeah, so hopefully you are very much clear about this example, which is very straightforward. Okay, let's have a look at the next example here. Okay, so in this question, it is related to the nonlinear scattering, the SBS and the SRS. Okay, so we are given a threshold optical power for stimulated brilliant scattering, the SBS, at a wavelength of 0.85 micrometer in a long single mode fiber with the injection as a source with the bandwidth of 800 megahertz is 127 milliwatt. Okay, so this is the threshold optical power for the SBS. Okay, the fiber is said to have attenuation of 2 dB per kilometer at this wavelength of 0.85 micrometer. That should be the attenuation of alpha, yeah, which is the attenuation coefficient. Okay, so by this information given here for the SBS, you need to calculate what should be the threshold optical power for the SRS, yeah, stimulated Raman scattering within the fiber at a wavelength of 0.9 micrometer, in which we are assuming the fiber attenuation is now reduced to 1.8 dB per kilometer at this wavelength. Okay, so previously we are working on this fiber optics at 0.85, yeah, 0.85, yeah, for the single mode fiber at 0.85 micrometer wavelength, and the SBS, the threshold power of it is 127 milliwatt, and the single mode fiber is having a loss of 2 dB per kilometer at this wavelength. So next, by using the same single mode fiber, we need to obtain the threshold optical power for the SRS, but this time the wavelength is at 0.9 micrometer, and the alpha, the coefficient of the fiber, is 1.8 dB per kilometer. Okay, so that should be the question. Okay, by the information of SBS, you need to obtain the threshold power for the SRS. Okay, so basically to answer this question, you have to go back to the application of the threshold power equation, yeah, that I did provide to you in the lecture notes before, in the slides before, yeah, the PB and PR, if you can recall back. Okay, so let's have a look at the solution for this example. Okay, okay, this is the one. Let's have a look at examples. Okay, this is the one, the solution for that example. We are having a 0.85 micrometer, bandwidth of 800 megahertz, the alpha is 2 dB per kilometer, and the threshold power for the SBS is 127 milliwatt. Okay, so this is the equation for the threshold power of SBS, and that is the equation, the threshold power. So we have 1 to 7, we just substitute the value. We have 4.4 times 10 power of negative 3. So the diameter of the core is unknown. Yeah, diameter of the core is unknown. So we just state that this is d squared. Lambda is 0.85 micrometer. The alpha, the loss, the attenuation is 2 dB per kilometer, while the V, which is the bandwidth is 0.8, yeah, 0.8, because the V is in gigahertz unit, yeah, gigahertz unit. So we need to convert the bandwidth into gigahertz. We are given in megahertz, so we need to convert to gigahertz, so it's 0.8, yeah. Okay, so from this, we can calculate that the D squared is 24.9, and basically the D will be similar to, or almost equals to 5 micrometer. So this should be the diameter of this single mode fiber. So from this D value that we obtain, we can then insert this value of D in this calculation of threshold power for this SRS, and it can be defined that the PR, the threshold power for the SRS, will be based on this equation. The D is the diameter, lambda is wavelength, and alpha is the loss, attenuation coefficient. So we're going to have the D is 5, the lambda is 0.9, and the alpha is 1.8, as stated in the question. So from this, we can calculate that the the SRS threshold power, or threshold power for the stimulated Raman scattering, is 2.39 watt. Okay, we note that when we compare the value of threshold power for the brilliant scattering, PB, and threshold power for the Raman scattering, the value is very much different, right? For this stimulated brilliant scattering, SBS, the power is 127 milliwatt, which is small. But for the Raman, SRS, the value is quite high, which is 2.39 watt. Yeah, so for the threshold power of SRS, the value is significantly higher as compared to the threshold power for the stimulated brilliant scattering. And this is the case. Yeah, this is the actual case, practical case that we can see in the fiber optic communication, in which the threshold power for the SRS is always bigger than the threshold power for the SBS. Okay. All right. So let's have a look at another example. If we have another one, let's have a look. Okay, so we have another examples here. We have the step index fiber. Okay, exhibit the following parameters. Okay, the step index fiber of multimode structure, multimode fiber, with a core index of 1.5, relative index difference of 3%, the delta, if you can recall that, the delta of 3%, and operating wavelength of 0.82 micrometer. Okay, so we need to estimate the critical radius of curvature at which large bending losses occur. Okay, so this is about the macrobending, yeah, macrobending effect that we have learned previously. Okay, so we are given this information here, a multimode fiber with a core index of 1.5, relative index difference of 3%, and operating wavelength of 0.82 micrometer. Yeah, so need to estimate the critical radius of curvature. Yeah, this is to estimate the RC that we have seen the equation before. Okay, and for the next example here, we just proceed the example with the question first. Yeah, for the next example, we are having a 40-kilometer long optical fiber link, which has a loss of 40 dB per kilometer. Okay, we need to determine what should be the minimum optical power level that must be launched into the fiber to maintain an optical power level of 2 microwatt at the receiving end. Okay, so this is about the application of coefficient alpha calculation. Yeah, calculation of alpha need to be based on the equation. Okay, and number 2 is the required input power if the fiber has a loss of 0.6 dB per kilometer. Okay, So this question, the next question is more towards the application of alpha equation. Okay, so we're going to see the solution after this. But let us solve for this question first, which is on the calculation of radius of curvature. Okay. Okay, so let's have a look at the solutions here. And this is solutions that we have here. So this is the information given from the question. Multimode fiber with an N1 of 1.5, that's a core index. The lambda is 0.82 micrometer, and the delta, which is the relative index difference, is 3%, and it's equal to 0.03. Yeah, 0.03. Hello?
Tak nampak slide.
Oh, tak nampak slide? Sorry, yeah. Let me... You cannot see the slide clearly. Sorry for that, yeah. Error occurred when screen sharing. I cannot share the screen. What happened? Let me see. Let me try it one more time. Okay, can you see the slide now?
Yes, doctor.
Yes.
Yes, doctor.
Okay, now it's okay, yeah? Sorry, somehow I have a problem with my Google Meet here. Sorry for that, yeah? Okay, we go back to this solution of the questions. This is to answer about the radius of curvature problem just now. Okay, this is the information given from the question. We have a core index of 1.5. The lambda is 0.82 micrometer, and the relative index difference, the delta, is 3% or 0.03. Okay, so this information will be very important, will be very useful in calculation of this RC or radius of curvature. So this is the equations that shall be used. Okay, we have seen this equation before, yeah, when we learned about the macrobending in multimode fiber. Right. So this N1 and N2 relationship can be solved by informations of the delta. And we know that from what we have learned in chapter 2, relative index difference is given by this. Yeah, delta is N1 squared minus N2 squared over 2N1 squared. This is the relationship. Okay, and from this we can calculate the N2 straight away. Yeah, because N1 has been given. So N2 is the one that need to be calculated. So N2 finally can be calculated to be equals to, the N2 squared, the N2 squared is 2.115. So the N2 will be about 1 point something. Yeah, and so N2 squared is 2.115, which shall be substituted in these equations here. Okay, so by substitution of these informations that we have, your radius of curvature, the RC, will be 3, N1 squared will be 2.25, lambda is given 0.82 micrometer, 4 pi, and this N1 squared minus N2 squared will give us this value. So for that particular calculation, we are going to get the RC will be 9 micrometer. So this is a critical bending radius that must be avoided. Yeah, must be avoided to ensure that the large macrobending losses will not be produced. Yeah, will not be produced. The 9 micrometer is the macrobending radius of curvature size. Okay, then let's have a look at the next solution, which is if you can recall back, the case where we have a 40 kilometer length of optical fiber with 0.4 dB per kilometer. Yeah, I think I got mistakes there. It's not 40 dB, it should be 0.4 dB. So if I did a mistake in my question, so please correct it for me. It should be 0.4 dB per kilometer loss of this fiber optic structure. Okay, so remember what is the question? It is to find out what should be the input power level. Yeah, the input power level, so that the output will be at least 2 microwatt power. Okay, I repeat again. The question is, we are given this information, the length of the fiber, the attenuation of the fiber, and we are requested to find out what should be the input power that shall be pumped in, that should be pumped in at the input, so that the output power will be maintained at 2 microwatt. So this is how we solve for it. Yeah, so simply we just base the equation of alpha and end up we are going to get that the P in, which is to be calculated, will be equals to 79.6 microwatt. Okay, yeah, so you can see the difference here. For a 40 kilometer long with this particular loss, if you want to maintain a 2 microwatt, so the pump in laser must be having a power level of 79.6 microwatt, which is quite high. Yeah? Okay, and for the next question, we are now using the same fiber, but it can be said that the loss, the attenuation is now changed to 0.6 dB per kilometer. Yeah, 0.6 dB per kilometer. So we want to maintain the same output power, output power value, which is at 2 microwatt. So if the output is maintained at 2 microwatt with the change of the coefficients value to 0.6 dB per kilometer, so what should be the value of input power that shall be pumped in at the input fiber, at the input point of the fiber? So by this calculation, the input power that shall be pumped in is supposed to be 502 microwatt, which is very much higher as compared to the previous case. Yeah, because we can say that the previous fiber is 0.4 dB per kilometer, but now the coefficient is higher, which is at 0.6 dB per kilometer. This is why to maintain an output of 2 microwatt, the input power shall be much higher due to this higher attenuation of the fiber optic structure. Okay, all right. So hopefully you understand clearly about these issues of attenuation. All right. Is there any questions regarding this attenuation so far?
No, Doctor.
No, Doctor.
Hopefully you understand it clearly, yeah?
Yes.
Okay, good. So that will be the end of lecture 5. So alhamdulillah, we have done with the attenuation. Hopefully you can understand it very well. So allow me to take a break for 10 minutes. So what time is it now? It is 9:57. So allow me to take a break for 10 minutes. Not 10 minutes, it's too long. 5 minutes, please. 5 minutes, yeah? 5 minutes up to 10:05. We're going to start with this lecture 6, part 1. Yeah, lecture 6, part 1. The topics will be on the intermodal dispersion, dispersion of optical fiber. Okay, so we're going to meet again at 10:05, yeah?
Okay, Doctor.
Okay, thank you very much.
Thank you.
Okay, Doctor.
See you again then.